Okay, so here we have a diffraction question. We've got a set of slits which are separated by 0.24 millimeters. So I'll draw a little diagram here. One slit, two slits, and the slit separation there is 0.24 times 10 to the minus 3 because it's millimeters. We know that the wavelength, lambda, is 6.3 times 10 to the minus 7, or 630 nanometers. And we're told that on a screen, that is a distance 4.3 meters away, we end up with a pattern of fringes. And those fringes have a separation that we're going to have to try and calculate. So we're going to be using our double slit diffraction equation for this, which is that W is equal to lambda D over S, where S is our slit separation, big D is our distance from the slits to the screen, W is my fringe separation, and lambda is my wavelength of 6.3 times 10 to the minus 7. So it's just a straight plug and play one, this one. 6.3 times 10 to the minus 7 multiplied by 4.3 divided by, and remember it's millimeters, so 0.24 times 10 to the minus 3 meters. And when we plug all of that in, we end up getting an answer of 0.0113. Everything's given to two significant figures, so I'll give my answer to two sig figs, which would be 11 millimeters. You would get the mark if you'd put 11.3 millimeters as well. Then state the conditions necessary for two light sources to be coherent. So we only get a coherent diffraction pattern, a pattern with really noticeable obvious fringes, if the sources have the same wavelength or frequency, remember they are related, and a constant phase difference. It's very common for students to say that they have to be in phase. They don't, they just have to have a constant phase difference. If they're in phase, you'll get a diffraction pattern where you've got the fringe in the middle. If there's a constant phase difference, that pattern might be shifted a bit, but because that phase difference is constant, you will still get constructive and destructive interference.